All right, great. Hello, everyone, and welcome to a webinar being delivered by GoML on retrieval augmented generation and how it can be leveraged to probably improve your LLM applications build. Just a brief introduction about GoML. GoML is a very niche services provider in the generative AI application space. We work heavily with healthcare, life sciences, financial services, and manufacturing organizations across the globe to help them build their use cases on leveraging LLMs. Till date, we built close to 50 plus use cases. A lot of these have been built leveraging retrieval augmented generation, and we are going to probably share some of our experience in terms of how that can be used for building some of these applications. Very niche AWS consulting partner amongst the top 10 in North America and 20 globally. Thank you so much for joining everyone for this webinar. And I hope this is actually useful for folks who are planning to probably leverage RAG and other techniques for building applications. I'm just going to quickly bring up a few slides that we have put together. And we're going to get started with a quick, brief introduction of the presenters today. I have been joined in by Vishesh, who's the chief architect at GoML with us, and I will let Vishesh introduce himself. But a quick, brief introduction about myself. I'm Rishabh. I'm the founder and chief business officer at GoML, and this is primarily the second organization that we are running. The focus again here is to probably help customers in their GenAI initiatives. I've been in the industry for almost 12 years, working across the roles of tech. I started off as a developer, where I was actually working in building some of these applications from scratch for our clients. But in the last 7 years, I've actually been working across roles of technical consultation, consultative sales, and building partnerships, specifically focused around hyperscalers. And at GoML also, I have been working closely with our partners at AWS and other places as well as customers to build almost a $2 million business in the last 1 year, focusing again on how do we probably leverage some of these techniques to build large scale domain specific enterprise LLM applications, right? Vishesh, why don't you probably also spend a minute introducing yourself to our audience?
Yep, thanks. Hi everyone, this is Vishish. I'm working with GoML as a chief AI architect, where I help multiple clients across multiple domains to solve their complex business problem using generative AI. Most of these applications use RAG, prompt engineering, and different areas of generative AI to solve the problem statements. Uh, I have across a decade of experience working in the AI. I started working as AI researcher with multiple companies, mostly in investment banking, healthcare, edutech, and a couple of other organizations. So I've been under AI space from quite a long for uh, almost around a decade now.
Great, thanks Vishesh for that introduction. So for the next 45 minutes, what we have planned for our audience primarily is that we'll probably introduce you to various ways in terms of how different techniques can be leveraged today to help you customize and build your LLM applications. But today's session is going to focus mainly on retrieval augmented generation and how it's a powerful tool. What do we mean by retrieval augmented generation? What are different components, right? Then, Vishesh is going to dive deeper into some of the terminologies and tenets of building a good RAG model on top of your large language models and how this can be leveraged, and probably specifically two use cases where we have leveraged RAG successfully to build some of these enterprise use cases, right? So I'm going to get started right away. But before we dive deeper into what is retrieval augmented generation and how it is leveraged, I wanted to spend some time in terms of helping our audience understand, because these large language models obviously have been in use for a couple of I would not say couple of years, but probably for some time now, especially after the transformer models got famous with Google paper in 2018, right? But I think it came to a bigger forefront when it became more consumer oriented with the launch of GPT earlier last year, or probably late 2022 for that matter, right? And while all of us have used chat gpt and the likes in our day-to-day life, right, even from planning our day to probably getting responses for certain very specific queries, to building our ppts, to writing emails and whatnot, right, preparing for client presentations, what we I mean, to a large extent we still struggle to understand how we can leverage these large language models specifically for solving problems, especially at the enterprise scale, right? And what do we mean by that is that while these large language models out of the box are very good for interaction and generic use cases, like as I mentioned, probably preparing me for my day, or creating a grocery list, right, or probably helping me write a personalized email for my clients and so on. When it comes to very specific domain based problems, like we're working with this large manufacturing giant, right, probably the second largest steel manufacturer, and the problem that they have at hand is that they have a lot of their raw materials that come from the globe or across the globe, right? And they want to leverage these large language models for planning specifically on that data, so they can probably bridge the gap from the supply to the demand side, right? These large language models out of the box do not perform that well. That's when it's very critical for us to understand what are the techniques that we can leverage to help us build more complex, more domain focused, more enterprise ready use cases, right? And I'm going to start with the simplest technique, which is prompt engineering, right? And what do we mean by prompt engineering? And to a certain extent, all of us have used this, even when we interact with ChatGPT today, right? For very generic use cases, we are leveraging prompt engineering, because I'm actually writing a curated prompt, helping the model understand, or helping ChatGPT understand today what do I require from it, right? And in the simplest of the terms, right, what we are trying to do is we're trying to give maximum context possible, right, to the LLM to understand the use case that I'm trying to solve via curated prompts, right? And it could be as simple as, what's the weather today, right? It's a simplistic prompt that I've written, to solving very complex generation use cases, right, by building very, very curated prompts, right? And there are different ways that you can actually build. And I'm not going to dive deeper into different prompt engineering techniques, because there's another webinar that Vishesh and I have done together that dives deeper into prompt engineering. But just to give a simple example, it can be, as I was highlighting, it could be a simple, very simplistic prompt, what's the weather like today, right? To a very complicated chain of thought prompts, which is a series of prompts, right? That helps the model understand the whole context of your use case, right? To another, prompt technique, which is called few shot learning, where along with your prompt, you're giving actual output examples to the model, right, in terms of what it should be generating, right? So there are multiple ways that you can actually leverage prompt engineering, a very powerful technique at its own disposal. We are using prompt engineering to create enterprise level applications, including a very complex generation or image generation use case that we're building for our clients. But the advantage of prompt engineering is very low complexity, because all you're doing is you're actually building a series of curated prompts, either to chain of thought, chain of density, few shot learning, zero shot learning, to help the model understand what you want, which does not require any kind of coding skills. It doesn't require any kind of technical skills for you to do, right? But one, disadvantage that it definitely has is that it requires us, while it's a very low effort technique, it does require an iterative set of efforts, because you probably build a prompt, you probably send it to the model, right, and then you probably judge the output, and then you probably iteratively improve that prompt, add certain examples, as I mentioned in case of few short learning, right? So it's an iterative effort, right? It's very tough to get the first response or probably first prompt right? But again, the advantage is that it gives you a high level of flexibility. Today, if your use case or the underlying model changes, all you have to do is you have to go back, sit down, and probably redo your prompts or the templates of the prompts that you've created. And it's a very low TCO option, because you're actually consuming most of these either through probably paid APIs, right? Most of your models, you're not paying for hosting these models or probably building or integrating data with these models, right? But when do you use prompt engineering? When probably your use case requires a very low domain context. What do we mean by that? And I'll probably take an example over here, right? Suppose your customer wants you to build a model or an application that helps them generate images, or probably images of dresses, right? And this is an actual use case that we're building, very high quality dresses, right, for our client. It does not require to be very domain focused, right? Because the dresses or the images that are getting generated need not be in a particular domain. It's more of a horizontal use case where you're designing dresses based on the user's preferences, right? So such type of use cases, since they do not require domain expertise or underlying data, can be built leveraging prompt engineering. Which then brings me to the second level of, or second way of building, and this is going to be the focus today, is retrieval augmented generation, right? While we'll dive deeper into what does RAG do, but in short, with the RAG, what you're doing is the vast amount of data set that these models are trained upon, you're actually just leveraging the model's intelligence, and you're letting the model know that augment that data set with this very specific knowledge sources, the knowledge source or the data sources that I've built in a vector format, and leverage this to generate your outputs. Do not leverage the vast amount of internet or garbage data that you've been trained on. Just leverage this vectorized data that I've built to build very specific responses for me. The advantage, obviously, of RAG is that it is probably one of the most powerful tools for you to build good domain specific applications. It reduces or it helps you control the output of the model altogether, right? It does involve certain amount of complexity, but the biggest complexity is that it requires you to understand the whole architecture of the application. Someone who doesn't come from a technical background or technical know-how would face challenges because you have different components which we'll speak about. You need to understand vector databases, you need to understand vector embeddings, you need to probably write retrieval algorithms and so on, right? So it's not as straightforward as prompt engineering. It does require some amount of effort, but not heavy effort. But at the same time, probably if you look at all the models, this or RAG provides the maximum level of flexibility, even more than prompt engineering when it comes to your domain specific use cases, because each of your components are independently handled, right? You can probably change your vector databases or the data within the vector databases and not affect the whole architecture, right? You can just change your retrieval algorithm, not change the whole architecture. The underlying model can get changed, right? And you don't have to change your RAG use case, right? But when does it become relevant, or when to use RAG as a technique? When access to external sources, and I'll probably come what do we mean by that in the next slide, but when access to external resources is very, very crucial for your use case, right? uh, Coming to fine tuning, which probably is another extreme way of leveraging these models, but probably is still leveraged or used quite heavily, is when you do not build your model from scratch, but what you're actually doing, the weights that the model carries, you're actually updating the model weights with the use case or very specific domain data that you have on board, right? What does that mean is that you're not changing the model architecture, you're not building the model architecture from the scratch. You're leveraging probably one of these models, let's say Llama 3, which is Meta's open source model, but you're actually updating the weights, right, within that model with the data that you have at hand to give you very specific outputs which are very focused to your domain, right? It definitely involves a very high amount of complexity with supply chain data that they need, right? So they will not respond to this data particularly. And most importantly, the responses that we get, like, and you can always try, right? Chat GPT, you ask the same question twice, it might give you the relevant answer, but the response might be quite different in 99% of the use cases, right? So there's no predictability or repeatability of these outcomes, which could be a challenge when you start implementing this at the enterprise level, right? So these are some of the challenges that we have encountered heavily when we've started building these applications. But now, most importantly, how do we address these challenges? We'll come to that, right? But I wanted to introduce to you a very powerful technique which is called retrieval augmented generation, right? And I think we very briefly spoke about this in the previous slides. But what is a RAG, right? And very simply to put it, what I feel what RAG is, it's the generative power of LLMs combined with the ability to retrieve the relevant data. The biggest challenge, as we see in the previous slide, saw in the previous slide, was that these models, right, fetching the relevant data, right, for them becomes a challenge. They're very intelligent model; they can learn on the fly, they can generate data, but fetching the relevant data that is actually very important to me is a challenge for these models, right? Now, why that is? Because obviously, as I highlighted previously as well, is because they are trained on huge set of data, right? So obviously at a point, while they're very intelligent, getting the relevant data from this huge set of data becomes a challenge, right? So RAG helps us solve that, right? And I'm going to take a very, very different anomaly for you to help RAG, while we'll get into the workflow and the techniques of RAG, right? But I'll probably take a very different terminology or analogy, sorry, to help you understand that, right? Just imagine, right? You have, and there's something all of us have faced, right? Just imagine that you have a human brain, and that human brain has actually gone through a very generic set of training, and human brain in itself is quite intelligent, as you might know, right? And this is something that all of us do, right, during our education, right? So all of us are trained on generic concepts, right? When I did my MBA, I was actually trained on very generic financial concepts, marketing concepts, etc. Right, and I became very, or probably my brain became very intelligent in terms of understanding these concepts, right? But when I went to my workplace, right, obviously that workplace required me to understand very specific, workplace based data, right? So probably their HR policies, their sexual harassment policies, their client policies, right? So while my human brain was very, very intelligent, right, fed with this information, generic information during my education, could not respond to those queries because I did not have that very specific data, right? So what happened is that there was a training that was set up, or induction that was set up for 4 months, where I was then trained on all these policies, right? My human brain was trained on all these policies, right? And all these HR policies, sexual harassment policies, client policies, data privacy, security policies, very specific to the organization, were fed into my brain, right? So after those 4 months, I now, or while my brain's architecture remained the same, that wasn't altered at all, right? But now, very specifically to this, the contextual data of that organization, it has been trained on that, right? So now, when I got in front of my clients, I would probably specifically respond to these questions, which are very relevant to the organization, right? So I always use this analogy. These large language models are very intelligent out of the box, right? And that's something that they bring on the table. But then today, when you ask a question, they would go back to their database or their data set, right, of this massive data set, out of which some of this data set might be garbage as well, like racist data. And that's why you day in day out you hear news that Gemini generated racist images, or Gemini or probably Ultra responded to Michael Obama mission, sorry, Barack Obama as the first Muslim president, right? Because some of this is garbage data, because this is internet data, right? So the only thing that we're doing in retrieval augmented generation is that we are telling these large language models, Mr. Large Language Model, you're very intelligent, right? But I don't want, when I'm going to give you a question, I don't want you to refer to your data set, right, that you've been trained on, right? You just use your architecture and intelligence, but I'm going to give you my curated data set or knowledge source, right, along with my prompt. You leverage this data source to respond to my question. In the simplest of the terms, that's what RAG is, right? But then when we get into the complexities of RAG, where Vishesh is going to dive deeper into the architecture, it has primarily two components, right? It's got a retriever and a generator, right? So it probably follows two steps. It's retrieval as well as generation, right? Now, what does retrieval do, right? Retrieval primarily, is based on the input prompt that you're actually getting, right? It primarily gets the relevant data from the set of data sources, from the vectorized data sources that you stream, right? So the first task that actually does is, based on the prompt or based on the query from the user, it's actually going to get the relevant data from the data source, right? So now that it has the enhanced data source or enhanced concept, and I think the best model to probably replicate that is Google's BERT, right? It now goes to the generation or the generator, right? Where it has this prompt or the query from the user, but at the same time, it now has a very curated, data or probably enhanced data from that query. It's going to combine that and send to the large language model, right, and ask them to now generate the relevant response for the user's query based on this relevant context or this retrieval, this query plus the enhanced use case, enhanced data set that it has, right? If I get a little deeper into the steps of it or the workflows of it, what we just spoke about, right? So you've got your user input, which is primarily a query or a prompt that the user has given to the interface. But the first thing that this interface will do is this query is sent to search the relevant information, which is what the retriever would do, right? And what it does is sends this query to the knowledge sources that you've stored in form of vectorized database, right? Once this query is sent to these knowledge sources, a relevant information with the enhanced context, which is primarily the very curated data set, right, is sent back to this interface, right? Now, this interface will combine everything. Right? It will probably combine the prompt that the user had, the query, and finally this enhanced context that was generated from the knowledge sources, right? And finally, it is now this whole context is sent back to the LLM, right? And this LLM will now generate a response leveraging its architecture, its intelligence, right? A relevant response for the user's query, leveraging this enhanced context query and the prompt that the user had, right? So this, at a very high level, is the workflow that is followed by RAG. I'm now going to hand over to Vishesh to probably dive a little deeper into the architecture and probably cover two use cases that we have built leveraging RAG.
Yep. Thanks, Raj. Uh, I'm gonna go ahead and share my screen really quick. Right. So So I think Rishabh gave a very nice brief and introduction about what exactly RAG is. I just wanted to focus for a couple of minutes on why RAG, right? What is the problem statement that RAG is solving for us, right? Why not just use LLMs? So one of the major challenges with LLMs is they have limited memory, right? If you look like the most of these large language models, GPT, Llama, they have the thing that's called context window. They cannot accept the text beyond a particular context window, whether it is 4,000 words or whether it is, for some model it is 8,000 words or it is 32,000 words, nothing more than that, right? But usual in real practical scenarios, we do have massive data and we want to utilize LLM's capabilities on this massive data. This is where RAG becomes really handy and becomes the best approach to use this. Why it becomes the best approach? Because this is the algorithm that connects the retrieval and generation part all together. So when we and I think Rishabh already covered a high level architecture around it. I wanted to cover what exactly goes inside RAG, right? When we say retrieval, so we understood that the RAG is completely something. If we have to break out RAG, it is retrieval and generation part, right? And it is something that is built on top of your one layer before your LLMs. RAG comes there. Now I wanted to somehow dive little bit deeper inside what exactly do we mean by the retrieval part. So let's assume that we have a huge corpus of data, and the RAG process in a very high level workflow, it would chunk this data into smaller, it would break this data into smaller chunks for us. And this chunk also goes through a chunking algorithm, and then it converts these chunks into a vectorized format. The reason to convert it to a vectorized format is uh, the the search algorithm, the when we would be retrieving this data back, works really best on the vectorized format. So we store all this vector into something that's called vector database. Uh, and whenever there is a query that's been asked by user through LLM, this LLM then searches back to our vector database, tries to search the most relevant into this vector database, and then gives back to the response. That's what exactly is happening in retrieval and generation piece. And yeah, this is what I'll dive little bit deeper around all of these touch points. So if you look around here, and I'll spend just 2 or 3 more minutes around the high level usage of RAG, that whenever I, let's say I have this question, I type this question that I meet my spending goal last month, and I pass this to LLM. LLM then passes this question and it searches in across its knowledge, its complete knowledge base. From this knowledge base, the first RAG approach comes into picture, where this particular query searches across the knowledge base that what should be the most relevant information for this data, and it only passes that relevant knowledge to LLM because that fits into its context window, right? So that's part what RAG does for us, and then it generates an answer on top of that. So this is the architecture that we have for our RAG. Uh, that First is the knowledge base, first is the complete data that we have. That data then goes to a loader. From that loader it comes to some set of documents, and that from documents we implement a chunking algorithm that converts this document sets into sort of a little chunks, and then we embed this. Embedding is kind of a let's spend some time on the embedding machine. uh, this is the process we call it vectorization, where we convert chunks into a vectorized format. The way we do it, let's assume that we have this huge PDF, and we somehow break this into, let's say the PDF is around 100 pages. We convert this 100 pages into one page documents. Let's take a very simple example. There's a 100-page document, we convert into one page document. Each page I'm calling as a chunk. Now each page or perhaps each paragraph I want to convert into a vectorized format, because sourcing algorithm works really based on the vectorization format. That's how the process is working, works well in RAG. The way it the way we would do it is, we would convert this textual data into some sort of numerical representation. uh, how do you do that? It could be as simple as that. call A as 1, you call B as 2, you call C as 3, and you have all these alphabets into your picture, and you directly go ahead and embed that. That could be one of the easiest approach to convert a numerical data into a vectorial representation, right? But when we talk broadly, there are two ways, or there are perhaps three ways where you do it. There is one sparse way, one there is a dense way, and then there is a hybrid way. In sparse way, it is something sort of uh, first of all, I mean, it's understood that just naming it on A as 1, B is 2, C is 3 does not give you a leverage around the data. It does not actually convert into a actual vector representation. So we need some sort of context awareness around when we convert into vector representation, right? And when we do so, it needs to be something sort of, for example, one of the basic example for sparse vectorization is TF-IDF, where we let's say the word the word let's say LLM. I have this document which is about LLMs. The word LLM is coming into the complete document almost around 100 times. So the frequency where we embed this on the on the weights of their frequency, on the order of their frequency. So for LLM, the word LLM, I'm giving that the numerical representation as 1, followed by the second frequency, giving them the representation as 2, followed by all the words that I have in my data. I'm giving this 1 2 3 on basis of my frequency order, and this is the way I would vectorize them. That is one sparse way of doing it. Then there is one dense way, that where you use models like BERT, which are already pre-trained on sort of this task, which are semantically aware. For example, so when I take semantically aware, for example, there are two words we are talking about. One word is LLM, and one word is large language model, where we have these two words. Uh, this kind of mean exactly same thing, but if I want to do it with the sparse approach, it would give them two different weights, because LLM is occurring almost around 100 times, whereas the word large language model is occurring only almost one or two. So what I would have in the sparse way of doing it, LLM would have the numerical representation as 1, but large language would have the numerical representation as 100, which does not make sense, right? Because they both mean the same thing. They should have kind of a similar kind of weightage. This is where dense way of doing this come into picture, where there is some sort of semantic awareness around this data. So it considers the frequency, it considers a semantic relationship between the data. For example, LLM, large language models, and anything that is semantically similar to them would have similar kind of numerical representations. uh, and doing so, we would have the complete embedding a numerical representation for all our vectors. But even this wouldn't alone suffice the or cut the slack. What in practice or real what we call as applied machine learning or applied RAG approach, where we actually use something that is in production, is a hybrid approach, where you have this sparse and where you have this dense. You combine both of them together. You want the frequency also to be there into picture. You also want semantic awareness also to be there into picture, where I call it as a complete context awareness. I want my LLM to come at top. I also want that all the semantically aware with semantically similar to LLM also come at top. So this is where you see in production we use something that's called hybrid embedding models. Now let's I would also take one step further deeper into vectorization and the vector spaces. So what exactly happens when you convert this textual data into sort of lots? So for example, I have this paragraph, I have this complete one pager document, and I have created almost around 10 sentences. There are 10 sentences in this complete PDF. In all these 10 sentences, in some sort of way, I have converted every word would have a numerical representation. So every sentence would represent in such a way that I would have a some coordinates around it. It would be something sort of 1 1 2 0 4 5 6, something sort of this, right? And when I have done that, how do you how does it help the complete algorithm? The way it helps is, now it would convert this complete vector into a graph like spaces. All these points would become your coordinates. Let's say the first coordinate, it would be x y z, z1 z2 z3, and all sort of vector spaces that we're talking about. uh, so now whenever instead of searching, or instead of actually searching it, whenever we want to retrieve the data out of this complete vector space, it becomes really handy and easy, because now when I have some everything in a mathematical representation, I just need to calculate the distances between this vector, uh, differences between this numerical representations that we are calling as vectors. That becomes really handy, because it becomes a complete cluster of information that I can retrieve from it. I'll actually dive a little bit deeper around this once again later. But now, for the context, I mean, we save this complete vectors into something that's called vector databases. There are multiple vector databases. There are Pinecone, there is VV8, there is Chroma. And what to select when, I will also dive a little bit deeper around which database to select when. Uh, yeah. So this is something that we have already covered. Yep. So now the question comes into this picture: how this is actually happening in practice. Let's put all the pieces together. Now it starts with two. There are two open points over here, right? First open point is that you already have your knowledge base. You already have your set of document or data that you have, and now you want LLMs to only answer from that piece of knowledge, right? You have to utilize that complete piece of, maybe, let's take an example. It's an HR policies. You have this multiple policies for a company, and you want your LLMs to only answer on that data. uh, and the second endpoint is question, the question that you want the answer on. The way it would function is, first of all, you uh, there is a RAG approach that has already happened before the time, because this is not something that happens on fly generally. People already have created vector databases that already resides in your database somewhere. That and only the retrieval and generation process that happens on fly. So the vector databases are already created. So your knowledge base, that's let's suppose that are in PDF, you have already converted them into a vector database process. You have already done the chunking process back in the time while you were developing it. You have embedded it, you have vectorized them, and you have stored them into vector databases. Now the thing that is happening on fly is, whenever I ask a question, this question again goes through this question again goes through a RAG approach, which converts this query into again a numerical representation using the same embedding model, and then it searches across the vector database that we have. It figures out everything that is relevant to it, and then it passes. And now let's say the context window is 4000 words. LLM only accepts 4000 words. Now it would figure out everything that's under 4000 words. I mean, combined data of about in 4000 words, all the relevancy around 4000 words, and it would pass to LLM that this is all the knowledge that you have to use to answer this question. And this is the way LLM would say, okay, now this is some augmented answer. It's not an original answer that LLM would give. It an augmented generation. And then from there we would have an answer that this is the relevant data and this is the answer. So yeah, this is what RAG is in actual action. And now I want to actually dive into little bit technical area of this. So what I have created is a very basic uh, RAG pipeline that I have. So I have this normal PDF, and I'm going to start with this normal basic, one of the favorite books is Machine Learning of 100 pages. I have this. And I'm going to create a RAG pipeline using this, where there would be a chatbot that you can have. You can ask any kind of question through this chatbot. And it's going to be a very simplistic process. I'll go through it. What I have essentially done is, so I have created a folder that's data, where I've stored this particular file. Then I've created one folder called RAG, where I have this two files, that's called data and that's called RAG. I'll actually show both of them this files, and let's dive a little bit deeper around what goes in this. So now we are clear that what we need for RAG is breaking this PDF down into smaller chunks, embedding that chunks into vectorizations, and then from vectorization there would be part of retrieving those, right? So this is a very simple search algorithm that we would be performing. So the way to do it would be, to store the vector we would need vector databases. To create the vectors we would need an embedding model. To chunk the PDF into smaller chunks, we would need a chunker algorithm. So these are three things that we need a chunker algorithm, we need a embedding algorithm or embedding model to convert this chunked text into a vector spaces, and then we need a vector database to store that vector spaces with us. So these are the three things that we need for the RAG process. And for here, for this example, I've used Chroma. Chroma is one of the really handy database that you can directly download on your local system. The data stays in your local system, it's not directly connected to your cloud. It's really handy for developing with small use cases. So I've used that into picture. For embedding models, I've used the classic OpenAI embeddings that works really well for a lot of use cases. And for chunker algorithm, I've used LangChain recursive character text splitter. There are multiple text splitter algorithms. If we dive deeper into what are the different kind of chunking algorithms, there are multiple chunking algorithms, but what comes really handy is the recursive character text splitter algorithm. So now, essentially, first what we'll do, we'll read the PDF, we'll pass that to recursive chunker algorithm, that is recursive character text splitter. Here there are some parameters to define the chunk sizes, chunk overlap, length function, and this. What does this mean? This chunk sizes tells you that what are the chunk size that you want your chunks to be, right? And this is not a kind of a bypassed parameter. It is a really useful parameter, and I'll tell you why it is a useful parameter, because this there are a lot of things that depends on this. First of all, the latency of your complete program depends on this a lot, and the relevancy depends on this a lot. If I would have my chunking size really really small, I would end up with lot of vectors and such a dense database that it would become really really slow to feed or extract any information. That defeats the purpose of having uh, an LLM at your hand, right, at your fingertips. But even if I create a really really large chunk size, then the process of finding relevant data, right, let's assume that I have one word of my answer at page number 1 and one word of answer at page number 65, right? If I create the chunking of two only 50 pages, a massive chunk of 50 pages, I would never be able to pass this into LLM, right? And hence I won't have a relevant answer. So the finding the sweet spot about chunking is kind of a hyperparameter tuning, what we usually call that. It's something hit and trial. You load it, you try it with various chunking sizes and then see what works best. But usually start with something 300 to 400 words is something fine for PDF to start with. And this is chunking overlap that so now chunking overlap is kind of a parameter that is needed to link context between all these chunks. So this is a parameter that helps you that there are multiple chunks. How do you perhaps define the linkage between this chunking? What is the overlap parameters for this? So this is something that you can set as 100. Yeah, so there are simple parameters for this. It's very handy. So what I did first, I read my PDF, I passed that PDF into this chunking algorithm. That chunking algorithm is breaking this down into smaller chunks. And then after breaking down into smaller chunks, I'm using OpenAI embeddings to convert this into following the complete vectorization process and saving this into a Chroma vector database. So it's a simple process of chunking using OpenAI embeddings and converting and saving them into Chroma path. So if you see over here, Chroma directly have this what is a function in place or method in place that you can directly pass the OpenAI embeddings over here as the model. I just called it over here and I directly used it and directly placed my location of my where I want the vector to be localized or stored. So I put this as my location, and yes. So let's do it right away. I have this PDF and I want to start this process. So it could be as easy as just going and running this. So it would start the process and it would save this into a Chroma database. So you can see this, it's writing splitting 135 documents into 1016 chunks. Right, this 135 documents is just a normal random number, but the most important part is the 1016 chunks. That are the total number of chunks it has created, and it's a pretty fast process. It's not that slow. I mean, uh, just a process of creating an OpenAI embeddings and using that, it's not that slow. So you saw that, right? The 100-page documents got converted within couple of seconds, 2 to 3 seconds, into vectorized format. And this is where I can see the updated database that's stored for me, Chroma. So now the rack piece, the one part of creating the vector database is done. Now the second piece that comes into picture is retrieval of this. Whenever a query comes into picture, I just need to ask LLMs to somehow retrieve and figure out the relevant data from here. So the way to do it is also very similar, that whenever a query comes into picture, I need to again vectorize that, and then using this vectorize, I would go into my complete vector database. I would figure out whatever is similar to this vector and just pass that to a similar vector corpus again back to LLM and ask it to generate an answer for that. So the way, and I think we already this was the part I was waiting, that I would dive deeper into vectorization process. Think it on this space, that you have a lot of vectors, right? And if I want to actually say something that this vector is similar to another vector, what do I mean by this in actual, layman terms? This means that if something is similar, they must be closer when you numerically represent it, right? This is what it means in terms of vector, that if this particular sentence is relevant to this sentence, they must be closer in the vector spaces. And there is a very easy way to define distance between vector, that is cosine similarity. There are multiple other ways, but one which is really used right now is cosine similarity between these vectors, that how close these vectors are with each other. There is just a distance between these two vectors. There is a simple mathematical formula for that, and this is what we are going to use today with this, that this is a vector, this is the another vector, this is the cosine similarity. Hence, anything that is under the threshold of 30% similar, or let's say 60% similar to it, pass me all of that, and so that I can pass that to LLM. So this is what it would be doing over here. It initialized a process where it is converting the query that is given by the user to vector spaces, and then it is performing the relevant query search using the similarity cosine similarity part. And yeah, so we have used GPT-4o for our retrieval part, the or generation part. We have used GPT-4o omni for generation part. So this is the simple process that it is following. Let's see a very quick and live example how it looks like in production, right? So let's say I have this, I've created a very small Streamlit app for this. So so I just go there and run the Streamlit app. So yeah, I have this chatbot ready. Let me just try any of these queries. Yeah, explain RNNs to me, cite the exact specific that you're referring to, and way you write the prompt here. This particular example does not include any prompt engineering. It is the way it is, right? So it exactly gave me the relevant answer from my complete knowledge base, that RNNs are this, and this is exactly cited from the sentence. So for example, if I want to look at it, I would actually find the exact same sentence over here somewhere, uh, where RNNs are written. So this is the exact same sentence that it would use from there. I mean, not exactly same sentence, but it would use a reference from that, and from that it would construct an answer. So this was one of the very quick example with RAG. I mean, we are running out of time, but there was one small quick example too, where instead of you know uh, this was single pdf document, but in reality we do have multiple PDF sources. We do have plethora of this PDF sources. So there was this one of the news summarization use case that I wanted to do. Maybe if time permits, I'll actually start with it. The process remains exactly similar. There is no change in the complete coding process. I just go there, I just changed my data to data multi, which is the folder name that I've kept for this, and I just do the RAG. And this is the best part about RAG. It is completely modular. You don't need to change a lot of things into your complete infrastructure. You just need to go ahead and you know just pass the data that you have. That's it. Actually, I'm gonna take a pause now, and I'm gonna open a room for a couple of questions, because I don't want to run out of time for the questions.
Great, thanks, Ishish. I think that was a very detailed walkthrough for everyone who want to, understand that to a certain extent, right? So what we tried to cover, obviously, the business context of RAG, and then Vishesh dive deeper into the, how you technically implement it, how powerful a tool it is, right? Any questions that we have? I don't see any questions on the chat. So if anyone has any questions, happy to take up any questions. If you can type them in the chat. Yes, the recording will be made available. This will be on our LinkedIn channel probably in a couple of days once our editing team processes this and hosts this. So the recording will be made available to everyone. That's correct. So Yuvraj, what we do is we actually do a series of podcasts and webinars, and we continue to do that, right? And I think what we'll do is probably in on our LinkedIn channel you can actually go and get and all these are hosted and recorded webinars and podcasts that we do. So on our LinkedIn channel you can actually go and access all this data, but we'll continue to do that. The next podcast that we have planned in the next 15 days is more focused towards prompt engineering, and our marketing team is going to probably share the schedule as well. That's a good question, Ashish. You can always reach out to our HR. Thanks, Yuvraj, for the feedback. So, Ashish, just to answer that question, yes, we definitely are always on lookout for great talent, right? And we do have internship as well as full-time opportunities in the organization. You can reach out to the relevant folks again from our LinkedIn channel. We also have a contacts page where you can actually share your resumes.
Oh,
So, Vishesh, yeah, go ahead.
yeah. So I think the question is, if we summarize the news from the newspaper, do we need to handle the blocks of articles using CV or something? Uh, uh, I'm not sure that if I got your question right. So with CV, you mean the open CV, and you're talking about imaging part, the vision model perspective. Is that right understanding of this? Okay, perfect, awesome. Uh, the answer would be ideally yes, but over here we do have a leverage around using OpenCV. OpenCV is, I love OpenCV, but since you have vision models and you have modular racks, right, multimodal rack that we usually call into picture. Today we only cover the very basic textual implementation of rack. But we do have image representation. You can also pass images to rack. You also can pass image plus text into rack pipeline. So there are multiple ways we handle it. But to answer your question, we don't use CV usually in applied rack. We directly use vision models for it. How do you handle token limits? So token limits is something that's where the complete rack comes into picture, right? Token limits come into picture where so when you directly do prompt engineering, or when directly pass the complete data into your prompts, that's where token limit exceeds, right? But when you use RAG, you take care of this, that your model can only accept 4096 words, and then you pass that into and divide that chunking size into that. Okay, when we discussed about, is the prompt and context window same? uh no, context window is something which is fundamental to, which is something which is fundamental to a foundation or a large language model. Each model have their own context window. It is the acceptance, it is the input that they can allow. But yeah, they allow the input through prompt only. So in a way, that's right, they are the same thing, but it's just the boundary on the prompt size, that number of words that you can actually enter into prompt. When we discussed about the memory insufficient issue with LLM, we mentioned about this. Yes, that's right. uh, could
And then
you
I
also
think we
discuss?
have a question on the evaluation metrics and the validation methods. I mean, obviously there are multiple, evaluation metrics that we have like MLLU. It's very specific to domain, and there's a separate podcast that we planned for it. Right. I think with the paucity of the time, I don't think so we can cover that part in this call. But we have a separate podcast planned for this. All right. I think we are at the top of 1 hour. I really appreciate everyone joining in and Vishesh doing this with me. Thank you so much. And again, this recording will be made available to everyone on our LinkedIn channel. Thank you so much for joining in. And please, we look forward to joining you all joining in for our future webinars as well. Thanks, everyone. Thank you.
Yeah. Thanks, everyone. Bye.